So we are covering the top k problems, top k heavy hitters, and as part of that, we'll also be covering count min sketch algorithm. Yeah, over to you, Alex.
Yep, right here. So can you see my screen?
Yes.
Excellent. Okay, so what I would like to do is um, talk about finding top K entries in a stream and kind of walk through different phases of it where different approaches will work and see how they stop working and we move to another phase. Examples we all know very well. Given the stream of data, it's a log, like continuously appending data to itself. We need to find top k or top one um, key, and practically could be YouTube videos or game players or most frequent network connections or whatnot. Yeah, and non-functional. We know that k is a lot less of total number of keys. That's one given to us information, right? Typically, but non-functional requirements. Let's look at several generations of those. And I feel that it's good to discuss impact of requirements in timing. So if you can do it once a month, your life is very different if you compared to you doing it every 100 milliseconds. Precision also affects our choices, and sometimes we do not have choices depending on precision requirements. And properties of input stream, which will come handy to discuss and count min sketch specifically. All right. So let's start with the simple example of we have 10,000 keys. That would be example of a game. We have subscribers and we have 10,000 subscribers and we need to find top one or top five or top k, how many we need to do. This example is specifically small, right? Because 10k keys is small number. So it gives us options that we may start our discussion with. Okay. Even with this small example of 10k users, we still have to have pretty complex architecture for the solution. So I am abstracting ourselves of how game works, and all of that ends up in the producer to a queue. That makes our conversation focused on actually counting top, away from logistics of getting the stream into the system. So there is some system that is a producer to a queue. Kafka queue is very adopted uh, tool. We can all talk about how it works. And now we have a consumer. So for small number of keys, uh, you could handle it, assuming your network and memory and CPU capacity is fine. Even single consumer can handle it. And there in the videos, you would talk about sorting data through um, keeping data in a key value store, hash, dictionary, map, and then every time we update the dictionary, we also check the heap, and we're doing heap push pop after we get k, or heap push for the first k entries. Yeah. When we come to office, we need to, nobody will let us write those heaps because there are some operational nuances with that. So I brought up some technologies here that could help us. And I spent the morning today asking ChatGPT about Redis. Um, the challenge I would like to underscore here, because it's interesting to dive into the happy path is real simple. Redis has it's a key value store with extremely high uh, response rate. It can have 100,000 concurrent connections, and it can have uh, millisecond, single millisecond put and get operation. So it is very scalable for processing this stream. But when it comes to calculating the top K, you need to. This is still a case where we have precise requirements, This is, I didn't put it here. This precise answer needed. Precise answer. So for precise answer, you would need to scan all the keys, sort them, or put them in a heap. Don't have to sort, just put them in a heap, and then you have your answer. Um, so putting in a heap has two options. You can do it yourself, reading all the keys from Redis, or you can use Redis sorted set. The trade-off is that if you do it, you have a network overhead, and that quickly starts getting in the way of getting the data from um, key value store. And same will hold true for DynamoDB or any other key value store that you would use. With Redis and probably DynamoDB as well, you can use sorted cell and sort data as it comes by running increment call in Redis. And oh no, by running periodic job to just update the sorted set right in Redis. Then you do not have a network overhead, and you can easily meet 1 second latency. In fact, you can meet quarter second latency and have a reliability of if something goes wrong, you still have three chances to recover. Again, with production application, you would not want to have everything in a single host. So that's why there are multiple consumers here. That's why there is Redis has at least primary and the replica, and the query client will definitely read from replica to leave primary alone. Okay, so this is our first example. Do we want to ask questions and start discussions, or should we go to next example?
So, so you're saying, right, 1 second latency, right?
Yes.
How did you measure it? I mean, on what basis you are saying that? I mean, that is your require not.
That's my requirement to get precise answer, top 10 IDs, and the latency for that answer is expected to be 1 second. So give me answer as of 1 second ago. You have 1 second to do your calculations.
That's what I mean. Like, what is your underneath resources or underneath? I mean, how can you
Or
specify?
how can I justify that this approach will meet 1 second latency?
Yeah,
Okay, great. So I can share calculations. Basically, Redis can have 100,000 concurrency level, so you can have 100,000 clients connected to it. And in this case, you don't even need that. Sorry. In this case, what you will do is every 4 times a second, you will recalculate sorted set in Redis. You drop old one and make a new one. And sorted set calculation in Redis is much faster for 10,000 entries, is much faster than a quarter second. So you will have sufficient time to finish your 10K calculations because it is a basically single scan, but it's scan in memory on that Redis server. And Heapify is O of N calculation, right? So you can have your sorted set done inside Redis in less than a quarter second. And that will allow you to have you have a job that runs 4 times per second and keeps recalculating sorted set.
so you're saying your Redis will scale it out as long as the your stream is goes up or down,
No,
right?
no, 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 no. We are not talking about stream going up and down. We are very focused on a stream having 10,000 keys. That's very important here for top K because all these formulas are um, all these formulas will end up with log of n, and n is a number of keys. So for 10,000 keys, even single Redis instance will be sufficient. There is nothing to scale. But of course, for operational redundancy, we have master and the replication. Um, so you don't have downtime if master fails. And for 10,000 keys, a single Redis running on a reasonably average server, nothing too specific, too extreme, will do the job for 10,000 keys within 1 second, no problem.
You mean to say the 10,000 keys means 10,000 samples in a stream?
No, no, samples you can have as many as you want. You have a game and it has 10, you paid game, right?
Mm-hmm.
I pay $10 a month to play that game. And I
Mm-hmm.
have 10,000 users in that system. There is no more. There are 10,000 people who pay $10 per month. We know that keys are limited to 10,000.
So, I mean, can you take this example like YouTube, right? I'm watching a YouTube, right? You mean to say
Yeah.
every 10,000 for 10,000 users, it
No.
will give the top list?
No,
Is it
you're looking at YouTube videos, but think about 1998 when YouTube only had 10,000 videos. They didn't have any other videos. So million people watch it, but the videos only 10,000. This is very first example where even single node will work, and all the formulas are um, you need to either scan all the keys to get the you need to scan all the keys, and it's linear time with the key count.
okay?
So
So,
this is very small example with
yeah.
10,000 keys.
So you mean to is like, I mean, can I assume that 10,000? I mean, in case of YouTube example, right?
Yeah,
10,000 videos watching million users, right?
watching by 7 billion users, but only 10,000 videos.
Okay, okay. That's assumption. Yeah, that's a good point. Yeah,
Right. And this is very important for this top K problem
that's correct. Yeah,
because all the formulas will come back to how many keys you have.
correct.
Incrementing keys is negligible in many, many systems. But at the end, you need to count it. And there are many approaches, but the ones I wanted to discuss here will give you right answers, will not give you bogus answers. And then you'll have to scan keys, and
Correct.
that's why number of keys is very essential to how you deal with it.
So 10K keys is like what? Like, is it like 7 billion users or 10K video
10,000
YouTube?
videos is saying.
Yeah,
It's
7 billion users, but only 10K videos, and you're looking for top video, not top user.
Oh, okay. Top videos which are hit.
exactly,
Yeah,
yeah, yeah. That's a very key point to understand actually.
Okay, okay. So we are looking at the unique, okay, not the user base, but the unique uh, actual video or content based, which are the top hit.
So he
correct.
started with what's happening in the back end, how many are there. So based on that, maybe kind of reverse engineering. So he computes it. Yeah, that's a valid one. Yeah,
But I
correct.
thought originally in the top K problem, I think let's say in the leaderboard problem, they were expecting like let's say there are 1 million users playing the game, right? Which are
Yeah, yeah, yeah. See the scroll bar? We're gonna go down. Exactly.
so there we're looking like top K users who are with their scores on the leaderboard, right? So that is the
Yeah,
difference.
he has that. He's saying this is just a very simple case. He has all the examples down this page.
Okay, 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 got it.
Right. So again, in terms of leaderboard, it's a game, and this game that we're looking leaderboard for only has 10,000 players in this example, 10K number of keys.
Correct.
All right, great. So yeah, it is very small example, and what I wanted to highlight here, even with a small example, we would need to have multiple consumers for redundancy. We would not want to store data separate from calculating the sorted set or the hash. Sorry, or the heap because of the because of redundancy here and network issue here. So let's go down and increase our requirements. So summary here is we can use in-memory processing on this consumer node if you wanted to write it. We can outsource it to Redis to leverage scalable system, and we need to redundancy for operational stability. Okay. Here is some details that you're
Yeah,
asking.
just one quick clarification. If you go and go to this, uh, scroll up, please.
Uh-huh.
So in this Redis, right, you are saying that it is using some sorted set, a sorted set to
Yeah.
find out those things, right?
Yeah.
Yeah, but what is the underlying data structure that you are trying to refer here? I assume that Redis has this skip list and some hash table, and by using that two data structures, it is quickly giving you access to top k element. Is that how you're envisioning this? um,
So I was thinking of having two table, so having a table in Redis where we just keep writing frequencies, updating frequencies. So that table will have key over ID and observed count that we have seen so far.
Okay, I
So
see.
each of us in the call will have one ID, and then we have how many sessions we join. That will be number, and every time I have a new one, I increment the count.
So there is something happening on consumer side which would keeping a track of the existing IDs. For example, if it is a
No,
video
no, no,
ID.
no, no, no. Consumer will be really like two-line code. It gets ID and it calls increment by one in Redis table.
Yeah, that is what I'm saying. Some process running on consumer, right? Which is basically
Yeah,
reading
it
the
takes from the queue and
yeah,
it interacts with Redis to increment the counts.
right. So basically, that's the write operation involved here,
Yeah.
and at the same time, we have to also give out the top element. So there is a read operation is also involved, right?
No, 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 no. Consumer is consumer. It's just write to Redis. Then you bringing up good point. There should be no, no, not command. There should be another cron job that keeps rebuilding sorted set.
Okay. So we are basically building, we are writing, and then we are building the shorted set. I see.
Correct. We keep writing to one table,
Okay.
and every 250 milliseconds, 4 times a second, we keep rebuilding the um, sorted
Then
set.
what is the scale of this data? Sorry, I joined a little late, but I believe scale is around, can we say, um, kind of YouTube sort of scale here for
No,
this
no, no,
traffic?
no, no, no. If
Uh,
the scale increases, a lot of the things start breaking.
yeah, right,
So
right.
this is a very intro example of 10K keys. It doesn't
10K.
matter the counts. You can have like, 4 million per second each. That's okay. As long as you have enough time to write 1 millisecond write to Redis, as long as you have enough time to write that, the counts could be large numbers. But the keys are 10K because that will define size of um,
Hmm.
underlying table in Redis.
Right. But if let's say if this 10K number changes and goes to million,
Okay,
then
we
this
scroll
does
down.
this.
Yeah, 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 yeah.
Okay, I see.
All right.
I see.
So let's look at
Right.
the small example. So writing and reading to Redis, and yeah, is single millisecond, and similar to DynamoDB, they're about 10 milliseconds, and concurrency is 100K. So we can write very comfortably all these records as we need. Sorted set, we can recalculate 4 times per second. And with the 10K, it will be also very quick recalculation. We'll have enough to have 1 second. And what I wanted to show here is result that we, yeah, please.
കേട്ടില്ലേ
Yeah,
നീ ഇങ്ങനെ വന്നേ ഇങ്ങനെ വന്നേ ഓട്ടതാ இருக்கு
I think it's
ഡെഡിക്കേറ്റ് ചെയ്യണം
unremarkable.
പിന്നെ
Yeah, result that we get is accurate result. It's precise. And the other thing I wanted to highlight here, this solution does not depend on anything about the dataset besides the number of distinct keys. So it could be uniform. Yeah, hello, can you hear me?
Yeah.
Yeah,
I
I
can.
muted everyone. Sorry, Alex. Yeah.
No problem, no problem. Yeah. So I said there is this approach does not depend on distribution of frequency. It does give accurate result every time because we recalculate everything because our data set is extremely small.
Alex, you
So
have first line where it says consumer can use the Redis or a hash and Heapify. Can you elaborate? So we are using Redis or Heap.
no, it can use Redis, but it could also implement everything in the consumer side. The discussion will not change much. You can use a hash key, a hash like dictionary in Python or similar structure in a different language to update values in that dictionary, and then you will heapify manually when you need. Very simple code. You can do it yourself too if you don't want to use Redis.
Okay, that's an alternate too.
Yeah, yeah.
Maintain the top
So
gate.
yeah, so on a 10K scale, uh, whatever you want to do will work.
Yeah, that is a lead code problem. That is, yeah.
Yeah, yeah. All right. So
So
now
Alex,
let's
I
go to
have one, yeah, one question, like how we are making sure 1 second of latency? How we are making sure, like, can you elaborate a little bit? 1 second latency, how we are making sure?
because I will have a recalculate job running 4 times per second uh, through some scheduler to rebuild the sorted set. And my sorted set is within a second. For sure, you get within a second. 4 times you have, 3 times you can fail, still you have your sorted set. And that's your answer.
Okay.
You asynchronously, you have two processes. One is writing, one is inside the Redis you set scheduler and rebuild the sorted set. Or you have another external trigger and rebuild the sorted set. And you can do it very quickly.
So why do you need the sorted set? I thought sorted set is a data structure which will already maintain it in a sorted way, right? In a Redis.
Because, well, the reason is if you have multiple query clients, what if you have like, 1,000 query clients? You don't want to calculate same thing 1,000 times, right? You just calculate once and read the sorted set.
So what is heap for? Isn't that going to help us like the sort?
Yeah, Heap is, if you don't want to use Redis, you can use Heap and you do your Heap scans and Heap pops to get the results out.
So
So basically, is it okay to say that we need some sort of pre-processing either ways? Either we keep it Redis or like keep it heap. Heap tries to do the same thing.
Um, yeah, both of the approaches are similar. You will write to um, map to dictionary to hash or Redis log table, right?
Yeah.
And then you will calculate top k as a separate function call or API. And then you will get it either from your heap that you maintain as you're writing, or you will do it from Redis.
Okay. And isn't that the same thing that we get from the map reduce job? Like,
We'll get to map reduce job in a moment.
okay, perfect.
Sorry. So let me actually, we spend a lot of time on this case when it only has 10K keys, and with 10K keys, my cell phone probably can do it itself. So let's go to bigger case a little bit because maybe there is more interesting corner cases there. So now, can we scale to 1 million rows and maintain 1 second latency precise? That becomes challenging. So short story is you could, but it comes to the limits of your network and your cluster sizes. And it really becomes challenging in the 1 second latency and practically not a good commitment to make. So let's increase timing to a minute. So now we need to know uh, ranking top K, but we have 1 minute to calculate it. In other words, right now is 10:30. I need to know what was exact top K at 10:29. And I have this last minute, I will use it to calculate. Let's increase number of keys to 1 million now. So let's take a look what happens here. On 1 million key, you can still use the previous solution with distributed Redis instances. And that will work. But with 10 million, that will no longer work. So you will need to start sharding your data to shards. Okay? Um, in the previous picture, we had one line here where we store everything in this one Redis. With the more than a million keys, um, this rebuilding sorted set will start taking long time. So if you want to maintain um, So if you want to maintain that one, okay, sorry, I put some confusion in the document. Let's talk about 1 second latency for 10 million keys, right? So you would want to shard this Redis or shard your hash and heaps and maintain size of the each hash to about 1 million keys. So if you have 10 million, you would need 10, 10 sharded to 10 different independent heaps, shards that have their own heaps, and then you will combine the 10 heaps manually at a query time. Okay. I want to pause here for a question. So how to scale from 10K to 1 million? 10K to 1 million scales through bigger Redis set. How to scale from 10K to 10 million? That doesn't scale anymore, does not. There is calculations about network to get latency to get the data and sorting it, and the 1 second is not feasible at that point. However, sharding allows us to independently calculate top K for each shard. And at the shards of 1 million, say we needed 10 million, but we have 10 shards. Uh, all these calculations are still feasible on the 1 million level, and then we combine the shards together. Okay. Yeah, Sagar.
Yeah, this is a sort of like.
Interrupt. Uh,
Mm,
uh,
I'm sorry. Go ahead. Yeah.
yeah, I
What
just
else?
wanted to. Okay, I think go ahead. Go ahead. I will come back.
Yeah, yeah. I can think of like a map reduce, right, wherein you have this and 10 different shards. They are doing their work and then combining the results. It is as good
Exactly.
as that, right? Okay.
It's yeah, but in this case,
So,
MapReduce is kind of does it for you. But in this case, we're talking about kind of like home built MapReduce, if you will,
hmm,
where we shard on the consumer side, writing to different Redis nodes depending on your key, and then query client will get the n results and combine. Very similar to MapReduce indeed.
very good.
Um, Yeah, very
So,
similar.
so based
We're
on the
breaking the writing and read operations. So when we write, we just write to the right node, and when we read, we do the combination.
Alex, I have a question. So Redis has something called as Z sets. So those Z set, I think they can handle up to 1 million, right? So basically, what I'm trying to say, if we use the D set, do we still need to go for the sharding solution and sharding and connecting the results?
1 million, yes, but 10 million. For the 10 million, you need 10, 1 million. Uh, okay, so my experience, production Redis experience is very little. So if you worked with Redis and there is a suggestion, I read this when I was preparing for this talk. It's on the Redis side is very theoretical. On the Spark side down below, I can talk more production related things.
Okay. No, I was
But
just
here,
trying.
if there is a different approach, yeah, please. This is just my research this before preparing for this meeting.
Yes, yes. I mean, we are doing a collaborative effort. So there is also something called as Z sets. So that's what I was. I don't know all the limitations on that because you're using some kind of sorted set. So if sorted set and Z set is the same thing, then I think we are on the same page. But I think if you think that's a separate, then we just need to check it. Yeah.
Yeah,
yeah.
definitely.
So who has the next question on the time check? We have 35 minutes past, so we'll.
Yeah. So I was going to
Yeah.
ask a question. So since we're sharding um, the keys for each Redis server, so the the responsibility of locating the shard is now delegated to a leader Redis instance. Is that how it is?
For this problem, query client would need to, for writing, consumer will need to know where to write. Uh, And again, if somebody has Redis experience, then please speak up because I'm repeating things I read very recently. So, way I read it is consumer will know where to write um, in sharded implementation, but I may be wrong here.
Okay.
Yeah,
Yeah, I was curious about that, but yeah, I'll try to find it with GPT or Google search. Thank you.
yeah, yeah.
So Vinay, can you post that question in the Jitsi chat or
I
in the
will. I
on our
will.
on our WhatsApp? Yeah,
All right, thanks.
thank you.
Okay,
I
right,
wanted
great.
to post.
Let's move to closer to count, mean, sketch, and some other approaches. Um, if you have now a lot of keys and maybe even more than 10 million, you would need to use. We talked about MapReduce. So there is approach using Spark, which is based on MapReduce, which will allow us to get this, but there is no 1 second latency for Spark. Uh, so minimum what is practically uh, we can offer is multiple seconds, and I put it as 1 minute. What was proposed here to get exactly the question to address here is how to get um, exact results for top K. Uh, so we use in this approach you use Spark with medallion architecture delta table. What this means really is Spark has a Spark cluster with workers that subscribe to this queue, and these workers do nothing but, as in a previous example, write, but instead of writing to Redis, now they write to delta table. So we can manage um, much larger data sets. And they do nothing besides writing those um, entries to the delta table. And then periodically, we have a Spark cluster aggregation job, and the delta that uses the data in delta table to get us aggregates that we don't have to scan the whole thing. Delta table is partitioned and z-ordered. So every hour we can partition by hour and the minute, and every hour we can group by all the data that we wrote, consolidate with the previous total aggregate that we had for previous hour, and now we have aggregate for the hour. For the minute, we do same thing, but now only looking in the minute partition. And by partitioning the data, we really isolate what we need to deal with very effectively. Then we get data up to a minute ago. So intra-minute, you can use a query time to query the last partition that had not been aggregated at the query time. So with the latency requirement of 1 minute, this will work using a very simple job to ingest and aggregate. This is Spark streaming job. This is periodically scheduled job. And query client can be as simple as Spark SQL, just a select statement with couple of unions in it. Um, and this is a picture of how this is called medallion architecture, if you're interested in that, where we have raw table and then we have improved data. They have these colors of gold, brown, silver, bronze, silver, or we call it however we want, but we get raw data here, we aggregate it. It's very easy for us to reason and understand where data is and how to deal with it. Okay. So that is great with a good SLA of 1 minute or so, maybe multiple seconds, maybe 10 seconds. You can debate how big is your clusters to get different performance results. And but if your cluster is not as big as you want, then the latency will increase. Okay. So this is last approach that I wanted to present that gives you exact numbers. You are not having any assumptions about anything. You query and group by everything, and you have either approach doing it in memory on the client, or you use key value store like Redis, and then finally you can go to MapReduce. Okay, this is very simple, I think, right? So let's take questions about Spark to the end, and move to the move to the count min sketch. Yeah. Now assume we still have a lot of keys. We have a lot of keys, but we cannot afford 1 minute latency. What if we need intra-second latency? Um, if we have a really large number of keys, say network flows, source IP to target IP, it's 2 billion squared, right? I don't even know name for that number. So then this type of approaches may not have a good SLA. If your SLA is hours, yeah, that's maybe okay. But if your SLA is like within a second or quick, these precise approaches break. And we'll go to count min sketch. Okay. So count min sketch allows us to approximately track um, appearances of items in the queue. So they will just count the keys. It is a probabilistic structure, so it is not giving us precise answers of what appearances are, unlike previous approaches, which actually count everything exactly. But we trade here our precision, our properties of a data set, and our computation complexity. It is nearly all one actually, because your count min sketch ends up being a table that you fix before you start everything. So you really don't depend on how many keys will appear or records will appear, because your count min sketch is fixed. But you will get size of count min sketch depending on requirements for number of keys and um, precision that you want to calculate your results with, and properties of your key distribution, frequency distribution. Okay. Before we get to details of calculations, CMS is not right application if you need exact precise counters. If you pay $10 for every hit, CMS will overstate your results. And by how much is a different subject, but it will definitely overstate your results. However, if you are not paying $10 for every one hit, it's an excellent application if you can be okay with approximation. Yeah, with approximation. Let's talk about algorithm, and then we'll talk about how to calculate. It estimates number of times when item has been seen. And the way it's doing it, it has several functions it calculates, and it updates the counters based on those functions. We all saw the video, right? So we don't need to watch video now. Okay, so moving forward, the key takeaway here is you need to know what you want in terms of error and in terms of data set. Then you can define right width and depth of your table. Width is number of columns, depth is number of hash functions. There is formula in Wikipedia which can calculate how many columns and hash functions you need to achieve specific precision. Yeah, well, it's yeah, I'll share this document, and it's right here. Link is here. Yeah, I'll do it. All right, great. So let's now work through some example here. Assume we defined our rows and columns, and for the conversation today, we should really look at like 3 columns and 2 rows. Otherwise, it becomes very time consuming. When we do, we have a matrix. Let's use Excel file, just kind of work through example. Um, okay. So we have here call 1 through call n, which will be 3 in our case, and function 1 through function n, which will be 2 in our case. So these are um, different hash functions. Diff hash functions. We have two of them. So I have ID equals 5. Let's give some cheat sheet for ourselves. Let's put here ID, and let's put here 1, 2, 3, 4, 5, right? And let's put functions f1 and f2. Okay. So here is this is my first hash function, and whatever that would be, my second hash functions, right? Whatever these numbers are does not really matter. At the end, we will use module 3. Okay, so that wasn't a good thing. Let's do. Okay, all right, and let's do this. All right, let's use module 3 to get 3 columns. So let's do this 3 columns now. Great. Okay, so now we know for every ID, we know where does it go. For function 1, this is function 1. ID 1 will go here, column 2. For function 2, it will also go here. And, this happened to be like this kind of like clear distribution, but in fact, they could be random. We can just mess it up, put 0 here and put um, 2 here. So they jump in the different places. So I get the idea of 5. If I get the idea of 5, my first function is 2, my second function is 2. I put here 1 and 1. And originally I set everything to 0. And when I get idea of 5, I put 1 here and I put 1 here. So the moment I put first ID, I already can answer many, many questions. For example, I have ID equal 28. Have I seen 28 in this table? Assuming 28 will not calculate to 2, right? And that's where our width and depth comes, to make sure that keys don't collide. We can say that no, 28 has not been seen yet here. So even with one entry, we can answer, if we have 10 million users, we can answer a lot of questions about all these users. Have they been seen? If we put another few entries, 0, 2, for example, right? 0, 2 for ID 2, right? So it will be 1 here, and now this become 2, right? What if we put 6 here, and that will be 7 here, right? We have 6 entries. We got ID 5, ID equal 5, and we get 6 times ID equal 2, right? We can already tell you who is the leader, who has been seen more than half the times, right? Because I know on average, I know average of entries, right? I can tell you that every entry writes 2 points in the table somewhere. It writes 1 into this row and 1 into this row. So my average right now is 3.5. I know who has been seen more than average times, who has been seen less than average times, who has been seen and who has not been seen. So I can answer these questions immediately with count min sketch. And this is mechanics of count min sketch. In terms of implementation, it's very simple. We have hash functions. which is I of them. In our case was 2. And this is formula, very simple formula. You append, for example, here to the string, and you calculate new function. And update will do what I just manually did in Excel. What I wanted to spend few minutes remaining on is nuances with collisions. As you see here in Excel, many rows have same values. For example, ID equal 1, ID equal 2 will write to second function 2, right? And so will 4 and 5, right? All these three IDs will add up to this number. So let's show example. Um, ID equals 4. Okay, now this guy came, ID equal 4 is here. It's a 1 and 2. Great. We're gonna add up 1 here, become 8 now. And here we put 1. All right. So we are getting the collisions and examples. Now, 8 cannot be attributed to um, a specific ID. Many different, 3 different IDs will all see number here. We can argue that these IDs will have other places in the first function. Yes, they will, but the same applies to the first function as well. There will be different IDs who contribute. So over time, this table becomes polluted. What are the options to deal with it? There are multiple approaches to dealing with it. Let's take a look. Okay, very use cases. Okay, this is papers. Now let's talk about dealing with pollution of the table and how to use it in practice. Yes, Agar?
Yeah, so just wanted to confirm, like these are basically pretty much approximations that we are doing, right? Probabilistically we are doing the approximation,
Yes,
right?
yes,
So then there is a chance that it could be more accurate, could be less accurate, right?
exactly. And that's why
So
we deal with the size of this table to ensure that our error is in acceptable range.
but then let's say if there are lot many collisions, that
Yes, let's talk
would that
about that.
affect would that affect the accuracy?
Yes, yes, yes. Let's talk about it. When
Okay,
the table is brand new, we have excellent results, right? When we put the first number there, second number, everything is super great.
correct.
But you saw now that this 8 now gets pollution from ID equal 4, right? Here. And this 1 belongs to ID equal 4, but if I put ID equal 1, um, so let's put ID equal 1, and then let's just do that quickly. We get 2 over here, and we get 1 over here, right? So now we have fully polluted table. And I purposely made it small so we can see this phenomenon. What to do with that? There are multiple approaches. One is this doesn't work, this does not work with uniform distribution of the data, because uniform distribution will pollute each and every cell and you will not get good numbers. So count mean sketch gives you very good results if you have um, elephant flows and mouse flows, which is some IDs are used a lot and some IDs are not significant enough um, to make numbers wrong. Yeah.
By pollution you mean like more prone to collisions, right?
Yeah, yeah. By pollution, I mean we write um, number in a cell based on multiple different IDs, and eventually every cell gets a couple extra ones incremented by. And so the number is not accurate anymore because different IDs here they come and write to all the cells. Even calculating mean still will be affected by a long tail that evaluates to different cells and keeps adding ones to those cells,
Okay, gotcha.
right? So what to do here? One approach is decay. How to handle uh, drift, drift over time. One is decay. Every hour you come and multiply all the numbers by 0.9. which means all the historical pollution will eventually become less significant. Very simple approach. You need to get precision and multipliers right based on your data set. Two is sliding time window. Sliding time window. Also very simple approach. We have multiple tables. And we start a new table. We have maybe 5 tables for every hour. Every hour we give up old table and use the remaining 4 tables, and we keep track starting from zero. But our time window that we can reason about is only, in this case, was 5 hours. Um, Number three is periodic recalculation using the full scan and the map reduce or Spark. Yes, there is a question.
Collisions still can happen in that time period, like, right? Or like within that 5 hour window, there is a
It will,
possibility that.
it will. But if you have, again, if your data is uniformly distributed, it's very quickly become polluted because everybody will say you have average. Everybody will just keep adding number to every cell. But if your data is not even, it's an exponential distribution where it quickly falls down with long tail, then sliding time window can just limit your probability of error to the amount you can live with them. Can it be done?
Okay.
Yeah, because the moment you get the first row, it's already polluted. Because one of the entries is in a place which will be needed later. Rucher?
Yeah, Alex. So you have only two hash functions, and I understand that if we can increase that hash functions, right, we can get a better outcome by doing so
Correct.
because
Hash functions
uh,
and also columns. You get more cells
columns.
in the table. That's why you need the typical examples you see in the videos. They all use 1,000 columns. In fact, the production may use much more if you want. But the subject is still remains. It's just easier to show with the 3 by 2. Sagar?
Right.
Yeah, isn't that we assume initially that the table size is fixed here, like whatever we are
It is.
creating. But then
It
if
is
we
fixed.
are increasing with more hash function, then the
Oh no,
whole
we are not increasing. We are just deciding before we start.
ah,
The
okay,
3 and 2 are silly numbers. We use maybe 1,000 or 10,000 columns and 5 or 10 rows for real data, depending on number of keys. In Wikipedia link, there is a formula. Kind of takes time to read through, but you can calculate how big your table should be. But once you start, you start. That's it. You cannot stretch it anymore.
gotcha.
Okay, this is really all I have. Excellent questions. It's I was preparing, I knew the question, and still I got so many questions that highlight how deep we should go. And thanks everybody for your questions. I'll have to give second revision and put that up there.
Yeah, thank you, Alex, for your time and preparing this level. It is much
Also,
appreciated.
one more thing, Alex, like here, most of the things that we were considering, like there is a real time calculation also that could happen here, right? Like
Yes.
heap is more real time than the uh, ready space approach that we took, right?
Well, this is fastest because it is fixed time. It's off one, right? You just if you need, you have to get top K. How do you get top K here, right? To get top K, you need K heap
Yeah,
that you maintain yourself together with this table. Now the question is, there is a new ID of like 3, right? That we never saw before. How do you know that ID should not be in a heap? That's where count min sketch comes handy. So
yeah,
you have heap, it has some IDs already. Now you're writing a new entry with ID equal 3, and you need to decide should it go in a heap or not.
yeah,
Okay, for that you go in the count min sketch with ID of 3, 0, 0. In this case, that is 6 and 0. So minimum is 0. Before value was 0, so now new value is 1. It is not a candidate for top k of like 1 in this case, right? Because you have a higher
Yeah,
points already.
correct.
Yeah.
Yeah,
So that is very quick way to triage all the candidates to see if they should be in a heap. And once they are in a heap, they now live their heap life with the push pops that's happening there.
yeah,
And then a new candidate comes again. You try judges with the count min sketch, finding minimum. So for a tree, in this case, 0, 0, minimum would be 0. Check with the what is the minimum in a heap, min heap you have, which is first element, and then decide if that needs to go into the heap or not.
yeah. So maybe like whenever in the interview we would be taking end-to-end design. I think as an extension to this discussion, I think we should also discuss this thing, right? Like populating the hit, because like that would be the only the final output that we need, right, as an outcome, as a result response
Yes,
from this system. Like
yes,
that's where we are basically like the end goal is like to come up with that mean heap with whatever threshold we set to, right?
yeah. So let me add and to and. Okay, thank you. Any
Yeah.
questions?
And also I think the do you think that the map reduce part of like pre-populating the table and the values, does that make does that deserve an additional discussion here, or
This table?
initially we were talking about the sorted set versus the pre-calculation, right?
Uh huh.
Yeah, in terms of top k.
Yeah.
So here as well, like the how the map reduce aggregate like does the calculation and the pre-population of data.
Yeah. So this is example here. MapReduce and Spark are very similar, right? So Spark does it in memory. Uh, in this example, Spark has a built-in library to read Kafka queue, right? To subscribe to stream of events. And the first ingest job does nothing besides reading events in the data frame and saving them to the Delta table. It's up to the Delta table to deal with the partitioning. Delta table is a format provided by Databricks, is open source as well, and it will handle the partitioning by hour and by minute. So that will create this raw table that is now partitioned, and this has the stream of events. That's the conversation we had before. What if billions of people watch these 3 YouTube videos that are there? We get a billions of rows here, all with the same. This ID here is different, but in that case would be the same, right? So this table is quite large.
Okay, basically
Then,
the horizontal scalability is what we are bringing in as part of
right,
the
and
partitions
in this case,
to.
uh, the replica counts on this table needs to be set. So because you have a hot spot in writing all the time, because you're writing to current partition, all the other partitions are completely like nobody touches them anymore.
Yeah.
Um, yeah.
And then
Um,
about the storage structures, like are we going like which choice of database in terms of like storages? So like are we just storing them as part of the key value stores, or like that could be an additional thing,
so
right?
in these examples with the MapReduce, I used Delta table, which is a Databricks format. It's a Parquet files basically,
Parquet, okay. So that
right? So
would be
this
more like in memory, or
no, they're on disk.
okay,
Spark processing is in memory, but Parquet files are written to the disk.
okay,
I mean, with all the caching and all that stuff, but they are on a disk. They are files. They sit in S3 buckets if you use AWS or Azure Blob Store if you use Azure.
yeah,
Um, and then this is raw data, and it's kind of like one-time use data. You write it and wait for the aggregation job, and the aggregation job comes every hour and every minute. And in fact, if I was more precise, I would should put minutes before an hour, because every minute you aggregate last minute, because table is partitioned, which means inside the table it's a new directory every minute. So Parquet files are also files, and individual parts of the Parquet table structure is actual like file on disk, and they sit in directories. So partitioning is nothing but setting up those directories,
Yeah.
and every minute you have new one. So you can aggregate this, and then aggregating by hour, it's much easier. Once you already aggregated minutes, you can just add them up. Right. So we have these two
That's
jobs.
Yeah.
Yeah.
And
you're
I
saying
think
the raw
that
table, right?
me,
The Spark maintains the global memory table, right? So that is what you mean to say the raw table.
yeah, the delta table. Yeah.
Delta table is on
Delta
disk.
table is different, right? It is not global memory table, right?
No, it's not in memory. It's in the disk. It's
Yeah,
a it's
yeah.
a it's a it's a HDFS file. In fact, you can use, right. Depends on your catalog, but Hive catalog can manage it, and it's a Parquet file.
So which
But
Uh,
one did you mention, Rini, then? Like, is it
no, first we don't write everything into the Parquet file. First, like, everything goes to the global memory table, and then we batch it out, or we based on the minutes or seconds, and then compute it, and that's how it is, right?
In this case, no. In this case, I decoupled completely. The Spark cluster, you can shut it down for 10 minutes if you want, right? What happens if you shut it down? Nothing happens. Q will just aggregate the records that need to be processed. Then you bring it back up. What is gonna do? Take all the records it did process and just write into this raw table. So there's, yeah, in memory there is some caching and things like that, right? But it really like goes to Parquet files.
But what is the latency? You said it's 1 minute at the batching here. I mean, it is not a.
Writing to the delta table, latency will be very small, less than a second. Writing to the delta table, writing the raw table itself, just keep writing records from Kafka, will be very quick, less
No,
than a second.
not that one. The computation, right? That means that this is not a real time stream. So on top of the real time streaming, are we computing that, or kind
Yeah,
of
and computation can be done within several seconds.
several seconds, right? Yeah.
Yeah,
Okay. Okay.
yeah, because the job is submitted and it's a batch job. So if you promise anything faster than several seconds, say 5, you will start pushing operational issues very, very heavily. It will not be stable. So you need to get SLA yourself for several seconds, just because of the batch nature of your aggregation job. Or this
Yeah.
query also, same thing.
Yeah. Because I've seen this kind of architecture with because one of our guys were using like 15-second delay, right? I mean, they need
Ye-
a result for 15 seconds. So then it'll go with the similar architecture.
We have pretty big pipeline at the office. It's really complex, and the
yeah.
timing there is about 12 seconds. I see
Yeah.
a lot of 4 seconds timings, but anybody outside of our team, we say 12 seconds, don't come to me before 12 seconds.
Exactly. Yeah.
Yeah.
I've seen like within a 1 second window, but they don't use this Spark.
Yeah, if you want 1 second window, you cannot use
Yeah. Spark.
this ingest job might be okay on even a less than a second, because it really doesn't do anything. It just kind of like configure a mini batch, and it will do it. But uh, this will not be sub-second. It needs to have multiple seconds.
Exactly. Yeah. Yeah.
But then if we go about a higher interval, then there would be lots of failed jobs, right? And the retries, and it would overall affect the throughputs, right? Doesn't
No, 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 no. That is
That second
in
part also.
practice is um, Spark's pretty reliable. So if there is a failed job, it will retry itself. We don't with the Spark, you kind of like away from all this nodes up, node down, and the cluster node itself go up and down. Spark handles it all. Yes, indeed. They do have handling for part of the job. They distribute job. If you look at Spark UI, it's really complex graph,
Yeah.
and they distribute job across workers, and these jobs, processed and contributed to like result collector. And if it doesn't, then a new node is spun off, and we've seen that happen actually. Node go down, and then the thing is retried on a different node. That all is true, but with the industrial tools like Spark, you kind of like have it.
The Sagar, it's, you remember the Disney, okay? So the Disney heavily using Spark, even for real-time streaming also today. Spark 3 they are using.
Yeah.
Uh,
So
so see,
um
is
go ahead.
see, yeah, one question, one thing that I want to bring up here, right? So basically, this is a disk, right? So we have right now, and here we have to live with 1 minute of delay or something, which is okay. But if it is a leaderboard sort of problem, wherein we have to display the scores real time, right? Or even let's say this problem where we have to show the top tier real time, then in that case, we may not be able to afford to write to the disk, right? We might have to do everything in memory, just in the interest of latency. So that is something which we can do as well instead of writing it to disk, right?
Yeah, but actually
Yeah,
this
let's
architecture,
see.
I mean, Spark architecture is depends on that. So if you see the Flink architecture, it's quite quietly opposite and than the Spark, but it does a lot in the memory actually. It provides, that is what it provides, a little better results than this actually.
Yeah, Flink is meant for the real time
Yeah, yeah.
purpose.
There's
Right.
a lot of in process, because a lot of in memory processing happening in the Flink.
Right. Yeah. So Alex, is it what you also think? Like, if we want to go real time, then we could just change this Spark to Flink.
We
Or
probably can. I don't have production experience with Flink, that's why I didn't do it. But I
But
know that
I
Flink
think
is much faster
in
than Spark.
I think in that
So
case, simply changing this, I think there is called as, I think, Lambda architecture that takes hold of, like, that's a parallel to the batch processing we are doing here. So I guess the answer is yes, but it would be slightly more number of components than just replacing this with some streaming component. Like in terms of Lambda architecture, I think some part they try to do in memory, some part they try to maybe do rerun of the jobs for the aggregation stage.
actually it is, I mean, in the real time, not many are, even not many are changing it, because Spark 3 they support, they saying like, the streaming is very good. I mean, real time streaming they support it, and it's as equal as Flink they're saying. Okay, but I never tested it.
so how is it happening in the leaderboard
I
problem?
don't. I haven't read the
Yeah.
Spark 3 architecture yet, but they're saying it's as good as a Flink. Okay, the Spark 3. I mean, Spark 3 architecture. Uh, but actually, the migrating from the Spark to Flink is, I don't. I mean, I don't know. Actually, it is a very
Mhm.
business driven decisions also, right? That is, yeah.
Yeah. Then I'm asking Alex about his research, right? That if you go towards the leaderboard problem, where you have to show real-time scores, then this architecture will not work for that, right?
this
Uh,
we need to balance precision and timing. So if we need a precise answer for leaderboard with
mm,
unbounded or very large number of keys, uh,
mm.
then you have to give it a time for something like this to lambda architecture batch mode to proceed and keep increments. Maybe you have lambda architecture, indeed you keep increments for like 1 second in the memory, and you have some other intermediate increments, and you keep recalculating this way, because count, mean, sketch, and all the other approaches, they have approximate introduction of a new item. Specifically, count, mean, sketch for sure. Calculating if a new item needs to be inserted in the heap is based on this, and this is approximate. So you can use it for leaderboard because of the speed at which you can calculate this is O of 1. But
CMS, it can be leveraged for that as well.
yeah, that's the count min sketch
Yes.
right here, right
Right,
here. Yeah.
right, right.
Um, but it is approximate. Because of the collisions, you will have inflated numbers, and even with decay and sliding window and periodic recalculation, it's just reducing error, but you're not eradicating error. So that's practically probably okay. And look at it, top videos. Do we really care which is like a top video? We we can live with approximation quite well, right?
Right.
Yeah. But in some other cases, if you do need precision, you have to have periodic jobs, and you of course break things in the pieces in something that has been pre-calculated already and something you need to calculate on the fly, and try to keep those two things together as much as possible. Um, yeah. Now I'm just like one of you. I'm reading it and I'm sharing it. I don't know. Maybe what I'm saying is
Yeah,
has issues also. Please, please, my sound confident voice. Don't take it as the true ground truth, right? Yeah. So
yeah, no, no, that's totally fine. I mean, we are all just collaborating here to share the knowledge that we have. But yeah, we can probably in future, Sagar, we can take it that
Yeah.
further as
So
later, right? Yeah.
yeah, so what I
So
had in mind is like all this which shares this Spark, Hadoop, or ATL pipeline or any kind of streaming. This discussion would come up. So I think that could be a good ideal topic for now, that as an applications of Hadoop, and so that we can find those patterns. We can very well take this up. Yeah, that's there.
yeah,
Or else,
and Srini, you also brought up a good point that Srini Flink is also a good
yeah.
candidate for this kind of thing.
So,
Correct.
Yeah.
So there
so
are aggregation problems as well. There are like the ad click aggregation is one of the topic. Like this is from
Yes.
Alex. That's a very important. Like most of the companies that ask that that one, because like it shares some of it with log monitoring, log aggregation, as well as any kind of observability system. So most of the observability teams generally ask this uh, these questions related to Flink or the batch processing. So maybe we can club them together anyway. Anything like, or we can discuss the Spark pipeline first, or like my bad, the batch processing versus the streaming pipeline first, and then go about discussing these things. So that so like trying to basically find the common patterns and be able to answer all the questions in one go.
Correct.
Right.
okay.
okay, guys, yeah, but not on the. We will see that. Okay, maybe on the weekdays, but not on these weekend classes. So um, I'm not sure. Okay, how everybody thinks, but yeah, it's based on everybody's interest. So when do you want to start that? We can definitely start discussing about the Spark and the Flink engines. Actually, that's a very very interesting topic, and actually much needed for most of these
Yeah. It
kind of
is applicable in many problems, right?
yeah
YouTube problems, let's say,
yeah, and
Google search, everywhere. Yeah.
it needs when especially it needs little bit of document reading also, and also little bit
Yeah.
practical knowledge also needs it. So I think one
Certainly.
or two can present it, but again, like I mean, I don't know. The presentation may go well. Okay, so we'll take some material. Better to read it. That's what my think is.
So how about let's say for example the leaderboard we can do right away. The end-to-end one, because this is much similar to like what we are discussing, right? Like using the
Yeah, Saga leaderboard and the top K, they all sound similar, right? But
yeah.
there is a subtle difference though. That's, I mean, there is a
Correct.
reason why they have individual designs, right?
Correct.
So I think it's crucial to understand. And even at click, there also we are counting. So all these problems we are just counting somewhere top K or
Exactly.
leaderboard top. So I think they all are very very similar. These, especially these three designs, at click, event aggregation, top K problems, and leaderboard. They all, and
Yeah.
they are overlapping also. So I think since we are covering, I think we should cover all the series, and they all will. Even if you lose track of these processing pipelines, they will bring
Yeah.
you back to the same thing.
Correct. Yeah. So like I think if everyone is okay, we can go about leaderboard maybe for tomorrow, because tomorrow we were thinking to discuss top K for 2 days, right? But we were able to wrap that up within one day. And thanks, Alex, for covering both one. So since tomorrow's slot is available, can we go about that the leaderboard then?
Yeah, it would be great if somebody also talks about leaderboard and yeah, I would like to learn because to be honest with you, everybody, that feels that I personally need a lot of practice. Like I prepared, I have my notes, I have all the
Yeah,
stuff. I come with this speech to the interview, they kick me out in 2 minutes. This next guy will not even come.
correct. One important again, the challenge that I felt here today was like to be able to squeeze in together all these things within just few minutes, like, so that could also help us, like, to find the patterns, common patterns, and only talk about specific things, like,
Let's do leaderboard tomorrow.
yeah. How about others, like, does that work with so basically, like, guys, let's prepare together in a way, like, so that we can have a healthier discussion, because these things are slightly tricky, as Aditya mentioned, like, some minute nuances comes in. mm, if we are prepared in advance, then only we will be able to have healthy discussion and ask more.
What is a real-time gaming leaderboard? Whatever we have in the
Yeah, top 25 problem, right? So again, to make it clear again, right? So tomorrow tomorrow we'll be discussing leaderboard, and like that's 90 minutes discussion, and most likely we'll finish it. Okay. So if any questions, we will push it to the next week.
So tomorrow is 9:30, okay, or you want to do 10 o'clock?
uh, let's go with 10. 10 should be better for everyone, like, to have a pleasant timing.
Okay. So I have a
Yeah.
conflict.
Anybody has any
10.
objections? I mean, yeah, we can.
Yeah, I will have to drop at 10:45, but yeah, I can be there for 45 minutes.
Okay.
Or maybe start 15 minutes. It's up to everyone. Okay.